And so I want to present sort of my side of the story for the oxygen tolerance of inorganic hydrogenases. I'm going to keep the introduction short because we're all lovers of hydrogenases. So there's really no need for introducing what inorganic hydrogenases are. And so the only thing I would like to say is my personal motivation to continue with this project. And that is basically making it to produce hydrogen for industrial purposes. And one of the grand ideas that I have in my head, and most of you heard of, is to couple hydrogenase to photosystem in some sort of phototrophic organisms. One of the primary ideas to use photosystem 1 and just tap electron out of the sort of the stromal part of that complex. And this is just a picture I shamelessly stole from Thomas Happe's review back in 2001. I think it's one of the best pictures even to date to show this. So anyway, so that's the idea. And as most of you know, we have a problem, right? Again, Thomas Happe showed pretty nicely in this JAX 2019 that the majority of inorganic hydrogenases are not tolerant to oxygen. In a sense, they degrade in the presence of oxygen. And that presents a huge problem for any sort of ideas of putting inorganic hydrogenase to use in phototrophic organisms. And so this is where I was when I started my assistant professorship here at Penn State. And ever since I left Wolfgang Klubetz's lab, I never thought I will work with hydrogenases again for this very reason. Academically, it's a great system to look at. Enzymatically, it's one of the fastest enzymes in the world. But as far as the application goes, there was this problem, okay? And so I kind of left it there for myself, for my personal career, until I saw this paper published in 2016 by the Italian group led by Simone Mora, where they claim that there is this hydrogenase from Clostridium beirinckii that can withstand presence of oxygen. And sorry, have some technical difficulties. Okay, yeah, so what they showed there was that enzyme can be fairly active both for hydrogen production and hydrogen oxidation. When you expose it to air, it's dead like any other hydrogenase, but then it recovers back full activity after you flash oxygen out. And that for me was mind-blowing. I mean, I've been working with hydrogenases with Wolfgang for a long time, and I never seen something like that. In materials and methods sections of that paper, I didn't see anything that tells me they remove sodium diethionate from solution. But even if it's there, these enzymes usually are not that tolerant. These things die regardless, usually. We worked with chlamydomonas ringhardi, with fluoricans hydrogenases, and none of them really survive oxygen for prolonged exposure to air, okay? And so this what triggered my interest. And so being first year assistant professor at Penn State is really great place to be because I have all the money in the world to do a new project and I can risk it a bit. And so another fortunate, hold on. Oh, there we go. Another fortunate thing was that Patrick Corrigan was very interested in trying this project. And so we got Clostridium beirinckii from slightly different species. But anyway, it's a couple amino acids different here and there. We put it into E. coli, delta SCR cells. We used PET sumo vector for that. And we expressed it, it expresses well. We activated with synthetic binuclear cluster that Patrick synthesized in the lab. Then we made sure that all the all the reductants are removed by desalting columns. Sometimes we do like a couple times just to make sure there's nothing there. And then we run activity assays. The basic one is just to reduce methyl viologen. And sure enough, it works. We lose activity. So don't get me wrong. It's not just all roses and unicorns here. It does lose some activity, but nothing close to what you would get from regular hydrogenases that I've been working with before. And so this is when I told Patrick, we should keep studying this thing. And studying we did. The first thing that convinced me that this enzyme is indeed special was this side-by-side experiment where we exposed CB-Hyd1 and CP1 to oxygen. We started with some mixture of active and inactive states. When we exposed to oxygen, CP1 flatlines, so it dies just like any respectable hydrogenase should. CB-Hyd1 just changed to another state. And that's the state that Simon Moore termed H-inact. And we saw exactly the same spectrum in our case. And then removing air by exposing to hydrogen converts back to active states. Beautiful. So this enzyme really just converts to this inactive state. And those of you who work with nickel iron hydrogenase know that that's what nickel iron hydrogenase does. It just converts this nickel B state, the ready state. And that's what you call oxygen tolerant hydrogenase in that part of the world. So anyway, so this looks very similar to me as nickel iron hydrogenase in that respect. Anyway, so we decided to see how stable it is. So we designed this little cell for ATR, attenuated total refractance IR, and we just flashed wet air through for like 2 days. And enzyme just stayed okay. Wasn't an active form, all right, but after about 2 days, we get just about 20% reduction in the overall signal in IR. So that really convinced me this is like a Rambo. It just doesn't die. And anyway, so we keep going with that. We did protein film electrochemistry. There are two important things that it showed us here. One, this is the red trace. This one is measured at 7.5, I believe. First thing it showed us that this is indeed a bidirectional enzyme. So around this midpoint potential for proton to hydrogen redox couple, it does both positive and negative currents if you just slightly bias it. So this really tells me it is bidirectional. And the second thing it showed us that at high potential, it just inactivates. Inactivates very well. This is actually at 100 millivolts per second. Sorry, I forgot to put details here. So it inactivates very quickly. If you try to do this with nickel iron hydrogens, you see almost no inactivation at that rate. And then reactivates back. What was very interesting was that this activation, inactivation potential was a lot lower than what you see pretty much in anything else. I mean, now we have examples from CP2 and CP3, as a matter of fact, but as far as back then, we didn't see anything else like that. I shamelessly stole traces from Patricia's work just to illustrate how different it is. So green trace here is her protein film voltammetry trace for disulfide Weber disulfuricans hydrogenase with sulfide in it. And even with that case, the E-switch potential, I know it's a kinetic parameter, but still, just to compare, that E-switch potential is quite significantly lower, about 100 millivolts lower. What that tells us is that this enzyme likes to inactivate. It inactivates very efficiently, quickly, and seems like it will inactivate just with a hint of oxidizing environment. And by the way, most of this was done anaerobic, so there's no oxygen present and still inactivates just fine. So that was that. Now, speaking of the DDH, this was about the time James and Patrick, they got their paper out showing that in disulfide Weber disulfuricans, you can inactivate with an aid of sulfide. And they shown that with an addition, you can get to this inactive state. There's a little bit of a confusion with the naming here, just for the purpose of this talk, even though first it was called HOX-air, this state here, then it was called H-inact in the second talk, second paper, and then, but because we have an inact as well, and we actually have not much of a clue of the structure yet, I'll get to that later, but this one we do. And so I kind of just want to separate that in the naming, and I call it H-inact as H, just so that we knowing that we're talking about different states. And here's why I think these are different states, because this actually scared me. Because, okay, maybe we have sulfide in our system, and that's really it. But the first indication that it's not the case came from IR. If you compare the IR spectra for DD hide AB, so DDH, and CB hide A1, the inactive state spectra looks slightly different. They're not terribly different, all right, but they're different enough to tell these are not the same states. And I don't have time talking about this too much, but believe me, it's really a real difference here. Now, one of the most telling experiments is doing protein film voltammetry in the presence or absence of sulfide. So again, Patricia's work showed that in the absence of sodium sulfide, you have much higher H switch than in case of with sulfide. In our case, made absolutely no difference one way or the other. So in that case, we can really say that the inactive state in Clostridium beirinki is not the same state as the one of Disulfur disulfuricans. And so what is the H inactive state then, right? And so we had a couple theories. The first one obviously was coming from the nickel iron hydrogenase field. We have this nickel B state, right? And we can have a hydroxide bound to the superon coordination side, and you can get it aerobically or anaerobically. The pathways are different, but the result is the same. So that was our one hypothesis, that this ligand that protects from oxygen is the hydroxide. The second part comes from this really bizarre behavior we observed in spectroelectrochemistry. Generally speaking, we just wanted to see the thermodynamic relation between different states and maybe figure something out from there. And what we observed was, first of all, that indeed we can easily convert to the inactive state at very low potential, okay, at neutral pH, as a matter of fact, which kind of confirms what we have observed with protein film voltammetry. There's no H trans state, doesn't mean it's not there, it just doesn't accumulate. These are steady state experiments, you have to keep in mind that. But what I would like to point out now is we observe H hide state accumulating in this particular experiment. And that is weird. Here's why. Under similar conditions, you can get H hide state from other species if you disrupt the proton pathway somehow. You either replace that cysteine that moves the proton in and out of the H cluster, or you can disrupt the proton pathway somehow, or you can saturate proton pathway by dumping a lot of hydrogen at very low potential, or you can completely remove the base for the proton from the H cluster altogether. Either way, you get the H hide state because hydrogenase just doesn't have any way to dispose of protons, okay? In our case, we do none of that. It's a wild type hydrogenase. It's done with neutral pH and at mild pressures of hydrogen. We usually have 3% hydrogen in our solutions. So why do we see the H hide state, okay? And that really bothered me for a long time. I mean, this is another example with pH 8.5. So even at basic pH, we can still get the same H hide state electrochemically. And so is the proton pathway disrupted? But it's really not, because I know this enzyme is bidirectional and it can work both ways easily if you bias it. So what's going on there? And this is what made us think there's got to be something about the proton pathway. There's some kind of an intermittent disruption that allows accumulation of the H hide state at low potentials. And the prime candidate for that would be that cysteine, which is still present in Clostridium beirinki. But we thought maybe it either moves out of the way one way or the other, but in any way, it cannot interact with the H cluster the right way. And then sort of to continue with that kind of logic, well, if it it rotates inwards towards the H cluster, why can't it bind it then? And so this led us to a second hypothesis for the inactive state, okay? And don't have time for this, but we did DFT to confirm that both of these are viable possibilities for us. And so we end up with basically these two hypotheses for what inactive state is. One is having a hydroxide, and this is really a ripoff of the nickel iron hydrogenase cycle. Or there's this cysteine hypothesis where cysteine actually binds directly. And so this is where we were in year 2020. Then in 2021, Thomas Happe publishes his paper where he shows crystallographic structure of Clostridium beirinckii. And I was absolutely happy. I know crystallography is not easy, and I'm a lazy person. I don't want to do it myself. Okay, so I was really happy to see we have a crystal structure. And sure enough, it was absolutely great to see that, you know, we have this flexible loop that harbors that cysteine in a different orientation than what you usually see in other hydrogenases. And Thomas Happe and his group gives a very good reason why. And we're really happy to see that. So cysteine most likely is participating in oxygen tolerance one way or the other. Here's the problem though. First of all, resolution of the structure was unfortunately not very good. The H cluster itself, you can kind of see the blob, but that's about it. And then the modeling of the iron sulfur distance, that's not right to me. I mean, that's my personal opinion right now. 3 angstrom is a bit too high for this to be an iron sulfur bond. For instance, in our DFT calculations, the iron sulfur bond for this cysteine model was about 2.3, 2.4 angstroms. Okay, way shorter than what this is. Now, granted, the quality of the data is not good to model it correctly, but still, it's kind of weird. So even though it's absolutely great to have this structure, but unfortunately, I don't think it can convincingly rule out one of our hypotheses in favor of another. Yeah, I can easily put an oxygen in between this iron and sulfur, slightly remodel the cysteine, and still get a decent fit to the density. So we need to get better structures, and either we do this or Thomas will come up with a better structure. Either way, I'm fine with it. But for now, at least, we kind of stick to our two hypotheses there. The only modification I would make is that probably cysteine is involved either way. And if the hydroxide hypothesis is the right one, then cysteine most likely stabilizing the this ligand somehow. Anyway, but regardless of that, what I really want to talk about today is that we will have this move. Okay, the cysteine cannot stay down. We know this is bidirectional enzyme that works fine. Okay, meaning this cysteine has to participate in reactions, right? So I think, and that also comes from the fact we do see the hydride state again, that the cysteine just a very floppy one. It can move around a lot. And perhaps the speciation is what is very quick and probably averages out over time. And maybe that's what is a prerequisite for inactivation. And so we try to find a way to see that speciation, okay? And I'm an EPR spectroscopist, thanks to Wolfgang, and we did EPR, okay? And this is very new data. We are about almost ready to publish this now. Here's what we observed. In both HOX and HOXCO states, these are the paramagnetic states we can look at that deal with binuclear site, spin density on the binuclear cluster. In both cases, we see speciation. In HOX state, it's very moderate speciation. The two species are very similar to each other. But if you're careful enough and keep your eyes open, you can see it. And now we have very good evidence that there is one. There is a speciation. It's much more obvious for the serine-inhibited state. The two EPR spectra are wildly different. So much so that for about 3 years, this gray shaded area I was attributing to 3-iron-4-sulfur cluster. I did not think that it was a CO inhibited state. But I'll show you that it is actually. So that's that, okay? So we have a species, okay. So now let's take a look at this a bit closer. First thing we did was pH dependence. And sure enough, there's a speciation variation between different pH values. Yeah, one problem though, it's not like you would assume pH dependence would look like if you have a one proton transfer in and out. You would probably have 90% at one pH, 1 unit up, 10% of a species. In this case, from 7 to 10, both species exist to some extent. At lower pH, at acidic pH, we get more of one species. At pH 10, we have both, sort of in almost a half-half proportions. So I don't think it's really the pH dependence as in protonation of the H cluster that way. And we also have other evidence for that in this case, okay? What was very weird is that, of course, we did the same thing with IR. And if we just focus on the HOX and HOXCO states, the bands are in identical position from pH 6 to pH 10. There's no difference. And so that's another reason why we think it's not a protonation, because Sven showed that protonation would change couple wave numbers. You change the charge of the H cluster by protonating. You have to change the charge of the binucleoside, right? And things will move around. In this case, we don't see any of that, neither in the HOX state nor in the HOXCO state. And it's all with the wild type hydrogenase with ADT, and we don't do any trickery here, okay? So that was weird, okay? Another weird thing was that at low pH, enzyme just turns to the inactive state on its own. And so we actually did pH 5 as well. I don't show it because it's just an active state regardless. So anyway, so that was that. So we decided, okay, maybe we need to dig deeper and find more from advanced EPR. So Patrick synthesized a carbon-13 labeled variant where we labeled the cyanides. And we did high score, both X and Q band. For the HOX state, we really saw no speciation at all. Those peaks are very narrow. And if there's any change in the electronic structure of the binuclear cluster, you will see it in this high score, and we don't at all. I just give you representative spectra here, but we did the whole 9 yards. Yeah, another problem was that, I mean, not a problem, but sort of blow to my ego a little bit. This couplings are very similar to those observed in non-tolerant hydrogenases. Like here I showed you the numbers for what Dave Britt did with Clostridium posterianum hydrogenase 1. You see those numbers, they're in a different order, but they're almost the same numbers, okay? So nothing in the HOX state tells us about A, speciation, B, oxygen tolerance, okay? Now, with the HOXCO state, we caught a little bit of a break. The two very different species of HOX CO states, they also have very different relaxations. So at low temperature, we can predominantly measure one species, and at high temperature, another. And so we took advantage of that and did iron 57 study. And by the way, thank you, James, for providing us the iron 57 labeled syntone for this. It was really kind. And again, no difference between low and high temperatures. So no difference between the two species. And overall, the spectra look very similar to what I have observed way back when for DDH, or more recently, James and Patrick, you were observing for DDH as well, and CP1 and Rin Hardy were always showing very similar pictures, okay? One more time, no speciation, no, nothing that tells about the oxygen tolerance there. Same goes for the carbon-13. Of course, we did that with the CO inhibited state as well. Again, this is the cyanide labeled carbon-13. Okay, we didn't do the CO labeling. Didn't really need to. Anyway, no difference at all. I'm not even gonna focus on this slide here. So here we have the problem, okay? We definitely have a speciation. We see it in EPR. It's pH dependent and everything. but none of the studies that focus on binuclear clusters show any difference between two species. So the problem is you have to think of an H cluster as a 6-iron cluster. And the electronic structure, as you see it by continuous wave EPR, is that of a combination of everything. When you look at hyperfine couplings or infrared spectroscopy, you're primarily focusing on what's going on the binuclear side, okay? I have just a little bit of time for this, so let me just make it a little bit more scientific here. So here's a little bit more complex way of showing this. So we have 3 primary spin systems in the H cluster. You have 2 9½ spins on the cubane, and if there's nothing else present, this is our antiferromagnetically coupled diamagnetic 4N for sulfur 2+ cluster. But the presence of a binuclear site with 1 unpaired electron there messes this one up electronically. So this coupling between the 2 subclusters mixes up the ground state so that stronger the coupling between the 2, more of the 4N for sulfur character you will see in the overall electronic structure of the ground state, spin state, okay? And it just happened that in the HOX state, this coupling is weaker, and the HOX-CO state is a lot stronger, okay? And so if there is any perturbation to the 4N sulfur cluster electronic structure, we'll see it more in the HOX-CO state than in the HOX state, okay? And so this is how you would explain why in the EPR, HOX state looks almost identical for the 2 species, just a slight deviation, but CO inhibited state has a drastic change in the EPR shapes, okay? And just to demonstrate that there are many different ways of doing this, I just picked up, built a program to make 5-spin Hamiltonian, and I put intrinsic G values for every component and only changed the ferrous irons, G tensor, and isotropy. And I just picked those up from the Ruber-Doxon study by Eckert-Munk. And as you can see, if I just change that in my Hamiltonian, in the HOX state, I have small change, noticeable, but small change in the overall EPR spectrum, but in the HOX-CO state, it's much drastic. So that's just to convince you that I think I'm on the right path here with explanation, okay? Now, and this part I would like to leave with just my possible explanation of what's going on. If you just compare 2 structures of hydrogenases, one Clostridium birinci and one CP1, right? And if you focus on, if you align everything as good as possible, you will see that this flexible loop is slightly in a different position. That's what Thomas Happel was saying. But the result of that is this other cysteine that coordinates the 4N for sulfur cluster seems to be pulling a little bit sort of on the side on one of the irons. And that would be breaking the symmetry and changing the geometry of that iron. And I'm thinking this is the reason why the electronic structure of the 4N for sulfur cluster has changed. And I'm wondering, again, pure speculation right now, okay? I'm wondering if the rotation of that cysteine, along with some flexibility in the this flexible loop, affects how the coordination environment of the 4N sulfur cluster is. And this is what we really see in the speciation of the EPR. Okay, again, it's pure speculation at this point. I wish we had crystal structure that we can trust with atom-to-atom resolution. We'll get there at some point. But anyway, so this is that. Now, if I have a couple more minutes just to show you the last part of my talk, it only takes another hour. It's okay, right? Okay. Anyway, so since we have this Clostridium birinci hydrogenase, we're already asking ourselves, okay, can we actually produce hydrogen? Okay. And we are very fortunate to have John Goldbeck just in the neighboring building here, who actually knows how to couple hydrogens to photosystem. And so we collaborated with him to see if we can actually do this. The 2 people that actually work on this project is Mike Gorka and Carol Baker. Mike is actually now employed by me. He's in my lab, and I'm really fortunate to have him here. So anyway, before we start with that, our first question was, we're trying to do cyanobacterial hydrogen production, I'm sorry. And the major problem there is in Silakov 702, there are no iron 9 hydrogenases. So the first hurdle for us is to actually get maturation factors. If we cannot get that, nothing will work regardless of what you do. And so we need to put G, E, and F in there. Fortunately, the rest of the system does exist. The glycine cleavage system is indeed present in cyanobacteria, not exactly the same one, so we'll still have to see how that works for us. But anyway, and Carol designed the operon containing all three maturation factors with their respective tags for specific immunoblotting. And I'm glad to report that we can express HYDEF and HYDE all in the same goal, really. And seems like we can get HYG expressing, but seems like something else is happening there. But Carol thinks it's because it's the last part in the operon, and we probably need to stick it with another promoter, so that it kind of works a little bit independent from other hydrogens. But anyway, so at least we are thinking we can express maturation factors in cyanobacteria. And that's actually under normal growth conditions for cyanobacteria, by the way. We didn't try to do anaerobic expression or anything. So, which is actually surprising, as a matter of fact. But anyway, and then the second part to that was how do we couple for the system to hydrogenase? And we have two ideas, fusing either to PSA-E stromal subunit. Nobody really knows what PSA-E does in photosystem 1, but it works. And the second one is fusing with PSA-C. That's the part that contains iron sulfur clusters, Fa and Fb, that are the final place for the electron until it leaves photosystem complex. So both have pros and cons. PSA-C has a problem to bind to the complex, PS1 complex. It needs C and N-terminus parts sticking in. So we have to sandwich our hydrogenase sort of in between. Anyway, as far as PSA-E work, it actually works. Mike Gorka did a great job synthesizing the gene, expressing it. This is E. coli expression, and then putting it into work with photosystem 1. And under light, it does produce hydrogen, so that's great. It seems like it binds with a 1-to-1 ratio, meaning addition of extra hydrogenase doesn't really do anything or much to the activity. The activity is lower than you would expect. The world record by the Golbik group is this number here, 220 100 micromole of hydrogen per milligram of chlorophyll. We only get 122, but it's a beginning. We are not there yet with the final work. And then as far as the PSA-C goes, the main problem was actually expressing it. I was very worried because everything has to fold properly for it to work. So we started with E. coli, and that was Patrick's work again. Seems like it does express well. It does have some activity. It's not great. For hydrogenase, this is extremely slow, but it does work. And we seem to have iron sulfur clusters there. And this is really the last part, last slide I would like to show. And this is the group, this is the money. And thank you all for listening to me. And yeah, I would like to take any questions if we still have time.